So today we're going to talk about the final physical application of integration that we will be studying in the course, and that is to find center of mass. Now, the situation that we're dealing with in this first part of the video is represented over here on the side. Imagine that I am, for example, a server at a restaurant, and I'm carrying a platter, and on the platter are all kinds of different glasses filled with drinks and plates with food on them. Where should I put my hand relative on this platter so that the platter is balanced on my hand? That position where I would put my hand to balance the platter is called the platter's center of mass. So consider the case that we have some collection of objects. Let's say that we have n objects in total. Let's say that the first object has mass m1 and it's located at a position described by the coordinates x1, y1. Likewise for object 2, it has mass m2, it's located at position x2, y2, and so on for however many objects you have. To find the balancing point, to find the place where you should put your hand, we can find the x-coordinate and the y-coordinate separately. And these coordinates of the center of mass are usually called x bar and y bar. You can find x bar by taking a ratio. In the numerator, take the sum from the first object to the last object of the product between the object's mass and the object's x-coordinate, and divide that by the total mass of all the objects in your system put together. Sum of mixi, sum of mi. And similarly, if you want to find the y-coordinate of the center of mass, you can just take the sum as I goes from 1 to n of mi times the y-coordinate of the mass and divide that by the total mass. Let's apply that to a simple example down below. We have a mass of 11 kilograms positioned at 3, 4, and a mass of 3 kilograms positioned at -2, -5. So what would the center of mass be in the very simple case of just these two objects? To find x bar, all I would have to do is take the mass of the first object, 11, and multiply it by the x of the first object, 3. And then go on and do the same process for the second object, its mass times its x-coordinate. Then divide that by the total mass of the system, 11 plus 3, 14 kilograms in total. So this gives us 33, take away 6 over 14. So this gives us 27 over 14, which is just a little bit less than 2. Now it makes sense that this weight, this center of mass, would be so close to the position of the heaviest object. The heaviest object is dominating here, the 11 kilogram object, and the center of mass will be very, very close to it. Likewise, for the y-coordinate, we can take the 11 kilograms and use that to apply to the y-coordinate of the first object, then 3 kilograms, the y-coordinate of the second object. Add up the two masses, and we'll get 44, take away 15 over 14. This is 29 over 14. Again, a positive number, very close to 4. Very close to 4, because so much of the mass is at that position. And that process can be extended to however many objects you want to deal with. Now in the next video, we'll be treating the case that we don't have n separate objects, but rather we have a single flat sheet, a single plate, maybe made of metal, but of an irregular shape. How then can we find the center of mass of an irregularly shaped plate?